Alright, so today we're going to look at the introduction to structural member properties. First one we're going to look at is the moment of inertia. It's a mathematical property of a cross-section measured in inches to the fourth that gives important information about how that cross-sectional area is distributed about the centroidal axis. What we're looking at is the stiffness of an object related to its shape. So, biggest thing you got to take away, the higher the moment of inertia is a greater resistance to deformation of the object. So what are we going to look at to the principles of it? So we've got beam A and beam B. A is like a joist, B is that plank, and what we're going to look at is they're both the same one, both made of Douglas fir, both of them are 8 feet long, but then the width, 1.5 by 5.5, or we can have the width of the plank being 5.5 by 1.5. Both of that cross-sectional area still being 8.25 inches squared. So when we look at the two, we go, okay, what is the difference between the two? Well, it's the same board, it's just rotated, whether it's a plank or a joist. So which one is going to have a greater resistance? Greater resistance, then, if we stand on it, which one's going to bend more? Well, hopefully you have stepped on some boards in your life, and the plank B is going to bend more than A. So that means A is going to have a greater moment of inertia once we do the calculations for it. So the formula for moment of inertia is the base times the height to the third all over 12. Or we should say that the height to the third times the base all over 12. All of that being based in inches. So let's go ahead and calculate it for beam A. That base is 1.5. The height is 5.5. 1.5 times 5.5 to the third gives us approximately 21 inches to the fourth. So the moment of inertia of beam A, 21 inches to the fourth. Look at beam B. We've got the base now is 5.5. The height is 0.3, since we're going to take 1.5 to the third. Multiply those out. We get a moment of inertia of 1.5 inches. So when we look at to compare the two, throw it into Inventor, put the force being applied to it, we can see that the moment of inertia of that joint is 21 inches to the fourth, while the moment of inertia to that plank is 1.5. So therefore, that A is about 14 times stiffer than B. So where do we take that information? We look at those composite shapes that we were looking at before. And why do we use an I-beam instead of a straight rectangular beam? Well, it has got about a third of the area, but it's only 1.5 its moment of inertia. So we're still got a moment of inertia that's comparable on a chart that's there, but the area is a lot less, so it's a lot cheaper to buy that composite beam than it is that full rectangular beam itself. And then when you're doing the other functions of weights and everything, you've got it better to use that composite beam itself. So once we calculate moment of inertia, that is just based on the area, that cross-sectional area. Now we've got different type of materials we can use to build that. So the modulus of elasticity is the stiffness of an object related to its chemical properties. So what do you want to take away with this? The higher the modulus of elasticity, the greater resistance to deformation. So what do we got to go through and look at? Well, we're going to look at two different joints. We've got A of Douglas fir, so wood, and then B, we've got plastic. Both of them the same length, same width, same height, same area, same moment of inertia. Nothing different between all of those. Both of them would have a different set of movement based upon which way it was laying, but both of these now, moment of inertia would be the exact same. What separates them? Well, if I take the plastic and stand on it, I would expect it to bend a little bit more than the wood would. So, A has a greater resistance to bending when that force is being applied to it. So how do we do and mathematically calculate that? We can go look at the modulus elasticity and look at the max bend depending on the force or load and the span between those supports themselves. So on the formula sheet, the beam deflection is equal to the force times the length of the object to the third divided by 48, the modulus of elasticity, times the moment of inertia. A couple things to notice here. On the formula sheet, F is also known as P. Both of those are representing the same. Either got the load or the force. And then making sure the length you're writing in is inches, because moment of inertia is in inches. So to cancel that out, we've got to make sure that length is in inches too. So let's calculate it for our two different pieces. Calculating the beam deflection, 250-pound person is going to sit or stand in the middle of this 8-foot board, 8 foot being 96 inches. 48 constant times the modulus of elasticity. You can look and Google that and find those different ones, or use inventor properties to find those, and then multiply that by the moment of inertia we have calculated. So 250-pound person standing on this board should deflect that board 12 hundredths of an inch. Look at the plastic itself. Plastic now, take the 250-pound person, stand them in the middle of this board. Due to the smaller modulus of elasticity, we expect that board to bend 0.53 or 53 hundredths. So we throw both of that into inventor again, look back at the deflection. That wood itself is about 4¼ times less deflection than what happens with that plastic. So that's where we can choose our materials and our cost depending on what we're trying to build. We have a bunch of different mathematical formulas to help us figure out how much weight it can hold and what different structures we should, or materials we should use.